Somewhere beneath several feet of solid Arctic ice, a submarine is moving forward in complete darkness, completely cut off from the outside world. No GPS signal can reach it. No radio message can get through. There's no sunlight, no stars, no coastline, nothing at all to look at and confirm where it actually is. Every wall around the crew is identical steel. Every hour blurs into the next, with no daylight cycle to mark the passing of time. The only sounds are the hum of machinery and the occasional groan of ice, shifting somewhere far above the hull. And yet, days later, that same submarine will surface at almost the exact coordinate its crew set out to reach. How does a 500-foot steel hull, sealed off from every possible outside signal, know exactly where it is when it has absolutely nothing to check itself against? The answer isn't magic, and it isn't luck. It's a piece of engineering so precise that it can track a ship's position purely by feeling every twist and turn it makes, second by second, without ever once glancing outside for confirmation. And the first time it was ever trusted with a real mission, it very nearly ended in disaster. Before that machine existed, submarines tried to solve this problem the old-fashioned way, and it went about as badly as you'd expect. In 1957, a submarine attempted to push north toward the Arctic ice cap, relying on nothing more sophisticated than a standard magnetic compass and basic dead reckoning, essentially estimating position based on speed and heading over time. For a while, it worked well enough, but the closer the vessel got to the pole, the stranger things got. Magnetic north itself starts to break down at extreme latitudes because the lines of the Earth's magnetic field converge and twist near the poles instead of running in the clean, predictable pattern compasses depend on everywhere else. The needle that had reliably pointed the crew in the right direction for the entire voyage began drifting, spinning, giving readings that made no consistent sense at all. With no reliable way to confirm their heading, and with unexpectedly shallow, uncharted ice conditions ahead, the crew made the only responsible call available to them. They turned back, roughly 180 miles short of the pole, half-blind and unwilling to keep pushing forward with tools that had just proven they couldn't be trusted where it mattered most. For the crew, it was a bitter kind of failure, the sort that comes not from a dramatic breakdown or an obvious mistake, but from watching your one dependable instrument slowly stop making sense the deeper you commit to a mission you can't abandon carelessly either. Turning around meant admitting that everything they had relied on for open ocean navigation simply didn't apply once they crossed into this part of the world, and that whatever came next would have to be built from scratch. That failure left everyone involved facing an uncomfortable question. If the compass breaks down exactly where you need it most, and there's no possibility of looking outside for a landmark, a star, or a signal of any kind, what do you actually navigate with? The answer had to come from somewhere completely different, not from anything outside the hull at all, but from precisely tracking everything the vessel itself was doing, every single moment, from the second it left port. Think about what it would take to know your exact location purely from memory, with your eyes closed the entire time. Imagine being blindfolded at the start of a walk through a building, with no way to peek at any point along the way. If you could somehow feel and remember every single step you took, exactly how far each stride carried you, and exactly which direction you turned at every corner, you could theoretically work out precisely where you ended up, using nothing but that internal record. That's essentially the entire premise behind the system engineers eventually built. Inside a sealed compartment, incredibly sensitive instruments continuously measured every acceleration and every rotation the vessel experienced, in every direction, thousands of times each second. A set of spinning gyroscopes tracked orientation, resisting any change in direction with enough precision to detect even the smallest turn. A set of accelerometers measured every change in speed, feed all of that data into a computer programmed with the vessel's exact starting position, and it could continuously calculate, moment by moment, exactly where the ship now was, purely through internal math, without a single glance at the outside world. It needed no radio, no satellite, no visible landmark whatsoever. It only needed to know where it started, and to never stop tracking every movement after that. There's a subtle but crucial detail hiding in that description, though, and it's the exact detail that would go on to define everything that happened next. Measuring acceleration and rotation is one thing. Turning that raw stream of measurements into an actual, continuously updating position requires the computer to essentially run a constant mathematical integration, adding up thousands of tiny movements per second into a running total of distance and direction traveled. Every single one of those individual measurements carries a whisper of imprecision, far too small to matter on its own, but stack thousands of them together, every second, for hours at a stretch, and that whisper doesn't stay quiet forever. The system that finally made this possible was installed on a submarine only months before its planned return trip to the Arctic, and that timeline alone should tell you how much of a gamble this actually was. The equipment had originally been designed for aircraft use, not submarines, and it had never been proven on a real underwater mission of this length or difficulty. Engineers were still working out bugs in the weeks leading up to departure. There was no backup plan if the new system failed partway through the voyage, no way to simply surface and check GPS coordinates, because GPS satellites didn't exist yet in 1958, and even decades later, once they did, their signals still couldn't reach a vessel submerged beneath the surface. This wasn't a controlled laboratory test. It was an unproven, barely debugged piece of equipment being sent directly into one of the most demanding navigational challenges on the planet, under enormous political pressure to succeed on the very first real attempt. The engineers who installed it had spent the preceding months in a near-constant scramble, chasing down false readings, recalibrating instruments that behaved differently on a moving submarine than they had during their original testing in an aircraft, and debugging software that had simply never been asked to run continuously for the length of time this mission would demand. Nobody involved could promise the system would hold up under real conditions, because nobody had ever actually put it through real conditions before. The only way to find out was to commit to the voyage and hope the equipment matched the confidence being placed in it. And baked into that entire system was a quiet, invisible enemy that never really goes away: drift. Every single measurement this kind of system takes carries a tiny margin of error, far too small to notice in any individual reading. But those tiny errors don't cancel each other out. They accumulate second after second, hour after hour, silently compounding the longer the system runs without any outside confirmation to correct it against. Picture a slow leak in a boat that's completely invisible from the deck. At first, it means nothing at all. But given enough time with no way to check and no way to patch it, that same tiny leak can eventually threaten the entire voyage. That's exactly the shape of the problem facing a vessel relying purely on inertial tracking under the ice. There's no way to know exactly how far the accumulated error has grown, because the entire point of the mission is running for days without a single external reference point to measure against. What makes drift such a uniquely unsettling problem is that it gives no warning at all. There's no alarm that sounds when the accumulated error crosses some dangerous threshold, no gauge on the wall ticking upward toward a red zone. The system simply keeps producing numbers with total confidence, second after second, whether those numbers are still perfectly accurate or have quietly wandered off by a mile or more. The crew has no independent way to check, because checking would require exactly the kind of outside reference the entire mission is designed to operate without. No radio call to make, no window to glance through, nothing at all beyond the numbers the machine itself keeps producing. In a very real sense, the deeper into the voyage they traveled, the less certain anyone could actually be that the dot representing their own position was still telling the truth. The voyage itself pushed straight into that uncertainty. The submarine dove into a deep underwater canyon off the coast of Alaska and began running submerged beneath solid pack ice for a sustained multi-day stretch, with no visual reference of any kind and no possibility of surfacing to check position along the way. Early in this kind of Arctic operation, the crew had already encountered unexpectedly shallow water, where charts suggested open, safe depth, forcing an abrupt retreat that revealed just how incomplete the available maps of the seafloor actually were. Now, submerged for real, running deeper into uncharted territory beneath solid ice, with zero ability to look outside, that same danger sat directly ahead of them. If the seafloor rose unexpectedly again, and if the navigation system's accumulated drift had pulled the crew's understanding of their own position even slightly off from reality, there would be no visual warning before impact, no way to see a wall of rock or ice rising out of the darkness in time to react. The entire success of the mission rested on a machine nobody could fully verify was still accurate, running blind, deeper under the ice with every passing hour, with absolutely no way to confirm or correct its own errors until the voyage was over. Inside the hull, the atmosphere during those days was tense in a way that's hard to fully convey. Every officer on watch understood, on some level, that they were trusting their lives to a black box that had barely finished being debugged, running a calculation none of them could independently verify, in an environment where a single miscalculation could mean colliding with solid ice or an unseen rise in the seafloor with no warning at all. Sonar could detect obstacles close ahead, but by the time something registered on a screen at the speed the vessel was traveling, there might not be enough distance left to react. The only real defense against that danger was the accuracy of a system nobody could fully trust yet, and the only way to test that trust was to keep moving forward through the dark and hope the mathematics held. That tension came to a head exactly where the earlier expedition had already been burned once before, in a stretch of water where the charts simply couldn't be relied upon. Depth soundings taken during the approach revealed a seafloor rising unexpectedly fast, far shallower than anything the maps had indicated, closing the safety margin between the hull and solid rock down to a distance that left almost no room for error in either direction. The navigator and the officers on watch traded terse, clipped updates, watching depth readings that seemed to shift by the minute, fully aware that a wrong call here would leave no time to correct course afterward. If the navigation system's silent, accumulating drift had pulled the crew's understanding of their exact position even slightly away from reality at that precise moment, there would have been no way to know it until it was too late to matter. For a stretch of hours, the entire mission balanced on the accuracy of a machine that had never been tested this deep into a real crisis before, with everyone aboard fully aware of exactly how much was riding on numbers they couldn't independently confirm. It's worth pausing here to clear up a common misconception, because it trips people up constantly when they think about how this actually works today. A lot of people assume submarines simply use GPS while submerged, the same way a phone or a car does. They don't, and they physically can't. GPS relies on radio signals broadcast from satellites, and radio waves of that frequency are almost completely blocked by seawater within just a few feet of the surface. The moment a vessel dives beneath the waves, GPS becomes entirely useless, no matter how advanced the satellite constellation orbiting above happens to be. It's also worth addressing another assumption people sometimes make, that a submarine could simply rely on sonar alone to figure out its position, the same way it uses sonar to detect obstacles nearby. Sonar is excellent at telling a crew what's immediately around them, but on its own, it can't tell them their absolute position on the globe unless it's actively comparing what it detects against a preloaded map of the seafloor. And even then, that comparison is only as good as how detailed and accurate that underlying map happens to be. In poorly charted regions, exactly like the uncharted shallows that nearly ended this very voyage, sonar alone offers no real substitute for a continuously self-tracking positioning system that keeps working regardless of how detailed or how incomplete the surrounding map turns out to be, which makes what was actually happening beneath that Arctic ice even more remarkable. There was no signal to fall back on, even if something had gone wrong. The system running that voyage wasn't a backup to GPS. It was the only option there had ever been for a vessel that needed to stay hidden and submerged for an extended period, and it remains the only option today. After days of running completely blind beneath the ice, tracking every turn and every subtle shift in speed purely through internal calculation, the submarine finally reached its target, the geographic North Pole, becoming the first vessel in history to do so. When the crew was eventually able to confirm their actual position against outside references, the accumulated drift from days of pure inertial tracking turned out to be remarkably small, a testament to just how precise this unproven, barely tested system had actually been under the most demanding conditions imaginable. It was the moment every open question from the voyage finally resolved at once. The compass failure that had turned back the earlier attempt, the untested equipment installed only months before departure, the near disaster in uncharted shallow water, and the silent, compounding threat of drift that had been ticking away the entire time. All of it converged into a single confirmed position, reached with pinpoint accuracy, using nothing from outside the hull at all. But the story doesn't quite end there, and the final piece of it is the part most people never hear about. Days after crossing the pole, when the submarine finally surfaced far to the east near Greenland, the crew didn't simply trust the machine and move on. They brought out a sextant and checked their position against the stars, the exact same method sailors had relied on for thousands of years before any of this technology existed. It was a strange, almost poetic moment, a brand new, barely tested computer built from gyroscopes and accelerometers being checked for accuracy against the oldest navigational tool humanity had ever devised. The two methods agreed almost perfectly. The ancient and the experimental had independently arrived at the same answer, and that agreement was the real proof the mission had worked, more convincing to the crew in that instant than anything the machine alone could have claimed on its own. When word of the achievement reached the surface world, it landed as a genuine sensation, proof that a vessel could navigate one of the most disorienting environments on the planet purely through internal calculation, without a single external cue the entire way. That breakthrough didn't stay locked to one historic voyage. The same fundamental approach, refined and modernized over decades, remains the backbone of how every submarine on the planet navigates while submerged today. Modern versions use far more sophisticated gyroscopes, some based on laser technology rather than spinning mechanical wheels, and they're paired with additional tools that help manage the drift problem more effectively. Sonar systems that can map the contours of the seafloor and cross-reference them against known charts, and brief periods at periscope depth where a GPS fix can be grabbed and used to correct the accumulated error before diving back down. Some modern systems also incorporate highly detailed sonar terrain matching, comparing the shape of the seafloor passing beneath the hull against preloaded maps to catch and correct drift without ever needing to approach the surface at all, which matters enormously for a vessel whose entire strategic value depends on never revealing its position. Ring laser gyroscopes, which have no spinning mechanical parts to wear down or introduce friction-based error over time, have also dramatically improved the raw precision available compared to the mechanical gyroscopes of the 1950s, shrinking the rate at which drift accumulates in the first place. But the core method, tracking every internal movement continuously and calculating position purely from that data, hasn't fundamentally changed since it was first proven under the Arctic ice. It remains the only navigation method that works with zero dependence on any signal from outside the vessel. and just as importantly, zero risk of revealing the vessel's position to anyone listening for exactly that kind of transmission. There's a strange irony sitting at the center of all this. We live in an era saturated with satellite navigation, where a phone in your pocket can pinpoint your location within a few feet almost anywhere on the surface of the planet, using a constellation of satellites orbiting hundreds of miles overhead. And yet the vessels that most need to know their exact position, the ones where the cost of getting it wrong could mean running into an unseen wall of ice or rock in complete darkness, can't use any of that technology at all. They rely instead on something far older in principle, tracing all the way back to spinning gyroscopes and careful physics, a system that knows exactly where it is, not because it can see anything outside, but because it has never, for a single second, stopped paying attention to everything happening inside. The next time you glance down at a blue dot on a map app, confidently pinpointing your exact location without a second thought, remember that somewhere beneath the ocean's surface right now, a submarine is solving the exact same problem with none of that convenience available to it at all, using math, motion, and nothing else, and getting it right anyway. That gap between the two, one world drowning in effortless, satellite-fed precision available at the tap of a screen, the other still relying on pure physics, tracked continuously from the inside out, is exactly what makes this particular corner of engineering so quietly remarkable. It doesn't rely on anything overhead. It doesn't need permission from a network of satellites owned and operated by a government somewhere. It simply keeps counting, endlessly, and trusts the count.